Hi, this is Jeff Spence, your Math 135 instructor for the Community College of Denver. I'm doing a video over hypothesis testing using the critical value method, or the critical value approach. This approach is a little more old school than the p-value approach, and it's actually a little harder, but it's actually more visual. If you like the visual steps of seeing what's going on, then this should make more sense to you, but it's still a little harder because things can get mixed up. Anyway, I've written the steps on the board multiple times, but here they are. First step, just like the p-value approach, you need the null and alternative hypothesis. The second step is where you draw the curve and look up the critical value. This is where you're either going to be using inverse t, or the t-table, or you're going to be using inverse norm to look up a z-score or a t-score. After that, you compute the test statistic using one of the three formulas we have so far. Once you compute the test statistic, you make your conclusion. If the test statistic is in the rejection region that you've drawn in step 2, then you reject the null. And if it's not in the rejection region, you fail to reject the null. So it's really going back to your picture and seeing where your test stat, your z data or your t data, ended up. So let's look at an example. It says, suppose in 2002, the average amount of points in an NBA game was 181 with a standard deviation of 14. You think that it's higher than that nowadays, so you sample 40 random NBA games and get an average of 201 points. Test your claim at the alpha equal 0.05 level of significance. Well, the null hypothesis and alternative we got to write first. So it says in 2002 the average amount of points in an NBA game was 181. So you write null is that mu equals 181. Okay, we get the standard deviation of 14. Let's jot that off to the side. 14. Okay, you think it's higher than that, so that's your alternative. HA is that mu is greater than 181, and that's what we're trying to show. That's a right tail alternative. Okay, so now well, let's read the rest of the information. So you sample 40 random games, n equal 40, and you get an average of 201 points. So X bar is 201. Test your claim at the alpha equal 0.05 level of significance. Well, we have our null and alternative, so now I'm ready to draw my curve, step 2, and find my critical value. So step 2, I draw the normal curve, and to look up the critical value, you put the 0.05 in the tail corresponding to the alternative hypothesis, so in the right tail. So 0.05 right there, shaded in, and that's our rejection region. Okay, so if our test stat falls in that region, then we'll reject the null. So we need to figure out what this cutoff line is right here. So in order to do that, in this case, since we're going to be using this formula, since we have a population standard deviation, we are going to do inverse norm. So we would do inverse norm .95 because it has left area, 0.95, and we'll get this z crit is equal to, let me do the inverse norm 0.95. Z crit is equal to 1.6449. Alright, then what we need to do after we have this picture, we need to compute our test statistic using the formula, our z data. So z data is your x bar, 201, which is our evidence, minus 181 over standard deviation of 14 divided by the square root of 40. What I would do is I would do 14 divided by the square root of 40 first, enter, and I get 2.2136 in the bottom. Then I would do 201 minus 181, which is 20, and take that 20, divide it by the 2.2136, and get 9.035. 1, sorry. Okay, so our z data is well beyond the critical value, which, it falls way over here, way to the right of that. So that is in the critical region. So since the t data is, since z data is in the critical region, you can see it visually, but it's greater than z crit, and we have a right tail, then we reject the null hypothesis. We have a lot of evidence to say that that the average has increased since 2002. All right, next problem. The average number of students in a CCD class in 2006 was 22.3. That's the null hypothesis. Let's jot it down. So h sub 0 is mu equals 22.3. Okay, we think it is different now, so that gives us the alternative. Different is a two-tail, not equal to, different. So not equal to 22.3. So we sample 35 random classes, n is 35, and get an average of 26.1. And a standard deviation of 9.8. So is this your sigma standard deviation or your sample standard deviation? Well, since it came from the sample, it's our sample standard deviation. It's in the same sentence. It came from that sample. So it's going to be an S, a 9.8. All right? And we're going to test the claim at the alpha equal 0.01 level of significance. So we're going to, we have our null and alternative. We're going to look up our critical value, so we got to draw the curve. And this time we have alpha equal 0.01, but it's a two-tail alternative because it's not equal to. So we take that 0.01 and we divide it by 2, and we get 0.005, and we put that in both tails. 0.005 there, and 0.005 here. Okay, now am I going to use inverse norm or inverse t? Well, since I have a sample standard deviation, I'm going to use the blue formula. So I'm going to be using inverse t since I have an 84. If you need to use the table, you would go down the 0.005 column and line it up with the degrees of freedom equal to 34, the sample size minus 1. I'm going to do inverse t. Oops, let me erase it. I'm going to do inverse t 0.005 and then the degrees of freedom, which is 34. That will give me this t over here, the -1. Inverse t 0.005 comma 34 gives me the -2.728, -2.7284. So that means that this one over here is the positive 2.7284. Okay, so after that you compute your test statistic. Remember, we're using the blue formula here. So I do t data. T data is my x bar, 26.1 minus 22.3 over the standard deviation, 9.8, divided by the square root of 35. Okay, so what I would do is I'd type the 9.8 divided by the square root of 35 first, enter. That's 1.6565. Okay, then I take the 26.1 minus the 22.3, that's 3.8, and divide it by the 1.6565. So divide it by 1.6565, and we get 2.293. Ooh, it's going to be 4.0. Okay. Now, what we do, we drew the picture first to determine whether our t data, our critical value, is in the rejection region or not. So is it beyond 2.782 or beyond -2.784? Sorry. And it is not. It's close, but it's actually not in the rejection region. It lays about right there. So this is where we say we fail to reject the null. And that's our conclusion. We have some evidence, but not enough evidence to reject the null and say that the number of students in a CCD class has changed since 2006. So critical value approach, a little harder. You have to draw your curve. That's the big important thing. Have to do that first if you're going to do the critical value approach, because then you compute your test statistic and determine if it's in the rejection region or not. The first one, 9.0351, was definitely in the rejection region. The second one, 2.2940, was not, because the cutoff was 2.7284. So not enough evidence to reject in the second one. So good luck, and we'll see you soon.